Hey, today I'm going to talk about a project that I'm working on. It's called as neural electronics. That is because it is based on electronics and neural networks. So if you are into research field that combines neural networks and electronics, you might probably know that you can take problem, solve it using neural networks, and use electronics to simulate the neural network. But this thing is different. It's different in the fact that we are not building neural networks, we are building electronics by using neural networks, as opposed to the first case in which we use electronics to build our neural networks and then train them and do crazy stuff with them. So, the main idea behind neural electronics is to create faster electronics and provide a model of neural network that can be used to create the digital components using any type of technology. That means it's not restricted to silicon that we generally use in our electronics. Using the neural network that we create with this procedure, we can use that network in any type of technology and create the digital components, or it can be an analog component too. So let's start with a simple AND gate. This is a representation of a single AND gate, simple AND gate. It has two inputs, A, B, and one output, C. So let's make another a neural network which represents this kind of input and output structure. So we'll have 1 and 2 for the input and one more for the output. We'll also label them as A, B, and C. If you know neural networks have something called as connected layers. So the layers of the neural network can be connected. They can either be fully connected, partially connected. So we'll have this network, since this is a very simple network, we'll make it a fully connected layer. Let's connect both of them. So this now here is a fully connected layer. This in this neural electronics, in this neural network, this is the input layer. So this is the input layer, this is the output layer, right? And you can actually have many other hidden layers over here, but since this is a very simple case, we don't need any kind of hidden layers over here, and this will work just as fine. Let me undo this one. Okay. So how are we? So how do we apply the concept that I told you, that is making this neural network behave as this digital component? How are we going to achieve that? You know that to make any neural network work, you need to train it. How do you train it? Using data. Now, where do we get this data from? We already have it. That is the truth table or the data output table of any digital component. So let's say, since it is a two input and you know that we have four combinations inputs, that's 0 0 0 1 1 0 1 1. The outputs for this will be 1 for when both of them are 1, and the rest will be 0. So now what we'll essentially do is take this training data and train the neural network on this data and get some kind of weights and values for each of these nodes. So since this is a very simple digital component, you need not actually train it. You can actually work the values out on a paper. But ideally, what you want to do is train this network on this data. So if you actually work this out on a paper, you can arrive at multiple different um, values or weights. That is what we call when a particular path in a neural network is given a weight. So that means whatever the value is coming inside that path will be multiplied by that weight. So you can arrive at multiple different versions of this weights that will actually satisfy this whole network. So there is not a single solution. There are a bunch of solutions. The it matters with what works for you the best. So let's say that this has 0.4 and 0.4. These are the weights, and the output layer, it has something special. It has something called as the activation function. So this has the activation function, and in our case we have specifically the step function. So let's say it's f of x, and we will make sure that f of x will output a 1 when x is greater than 0.6 and 0 when x is less than 0.6. So let's put in a value of 0.6 over. So essentially activation function is used to make sense of whatever is the input data. So the basic concept of activation function is you take in input data and you run it through an set of rules or a function, and you give an output value to that. And you'll see in a second why that is useful. Let me go ahead and erase this one. Okay. So let's take an example. Let's take one from this training data set and apply this as an input. Let's say we take this one, 0 and 1. So 0 into 0.4 for this set plus 1 into 0.4 for this set. So these both will get added at this point just before applying the activation function. So this will be 0 plus 0.4, and which will end up as 0.4. And then we will pass in this 0.4 into this activation function. That is f of x will be f of 0.4. Since 0.4 is less than 0.6, the output will be 0, which exactly matches our training data. Now, you can easily work out, let's say we take this data, we can easily work this out. Let's say, so this will be 1, this will be 0.4 plus 0.4, that will be equal to 0.8. F of x is equal to 0.8, and 0.8 is greater than 0.6. So we'll have an output of 1. Now that we have seen a simple example, let's try it out on a complex example and understand this topic better. In this case, we'll be using a 4-bit full adder. So a 4-bit full adder will have 4 different parts of simple adder, that is a single bit full adder, and we'll connect 4 of them serially to create a 4-bit full adder. So if you see this, then this one thing is a full adder, a single bit full adder. This is a single bit full adder. This is a single bit full adder. This is also a single bit full adder. So if you notice, we have 4 inputs of A, that is A1 to A4, and 4 inputs of B, B1 to B4. And apart from these inputs, we also have one more input, that is the Cin, that is coming from a previous calculation. That is the general use case. So now we know that we have 8 incoming inputs and 1 input from the previous addition. If it's not the previous addition, then this input is generally 0. And we have 4 outputs that we care about, and also 1 carry out, that is, if there is any carry, that will be forwarded to the next calculation or any other purpose. So now let's build our neural network by taking this input and output structure. So this is 1, 2, 3, 4. This is for our A, 1, 2, 3, 4. B, 1, 2, 3, 4, and our C. So this is our input layer, and we'll have one output layer. 1, 2, 3, 4, S, 1, 2, 3, 4, and a C out. So in this case, we don't really care about the intermediate carries that we are having, because we know the set of inputs and the set of outputs. We don't care whatever the intermediate steps are. We just care about the inputs and the outputs, so that we can train our neural network on that corresponding data. So here we can have an optional hidden layer, since because it's a bit more complex than the previous one. We can have an optional hidden layer. It can be one hidden layer, it can be two hidden layers. It depends on how much optimization that you want to do on the network. So if you consider this network, let me take, if you take this network into consideration, the computation time is directly dependent on the number of calculations that you need to do per full bit add. That means, let's say you take 1 second to, it's totally absurd, but let's say you take 1 second to do a calculation in a full bit adder. So the first two bits over here will go into a full bit adder and take a computation time of 1 second, and will give you the output into S1 and C1. And this will trigger the next calculation over here. This will take one more second, and then the output is as well as into S2, C2, and then again one more second, the output is S3 and C3, and then one more second, S4 and C out. So we have totally consumed 4 seconds of computation time. Though this number is not realistic in any way, this is generally in way less, as in nanoseconds or microseconds. But for the sake of example, let's consider this. So by this model, you can see that all of the computation here happens linearly. Here, this is happening serially, that is one after the other. Here, all of the calculations are going on parallelly at the same time. That is, all of this thing, let's say, also takes in 1 second. So all of this computation, whatever technology that we can use to build this nodal nodes, will take up 1 second. And if we have a hidden layer, this will also take 1 second. And then the output layer, this will also take 1 second. So the total time consumed for this will be 3 seconds, which is obviously less than this, which means it is better. So we have got 4 seconds for a 4-bit adder, but a general purpose computer always runs on, nowadays it always runs on 32 bits, right? So if you make a neural network that is 33 bits long and an output that is whatever the number that is, sorry, it's not 32, 32 plus 32 will be 64, plus one more carry in, that would be 64 plus 165, and then a hidden layer, whatever number of nodes that you want to use, whatever number of hidden layers you use. Generally, on the max, you will be using 2 or 3 hidden layers over here. That is the maximum that we would be going to create complex networks. And then here we have the output layer that will generally be again 33 bits for that case where we have a 32-bit computer, a full adder system. So in that case, this would be 1. This would be on the maximum, let's say it has 3, and this will take 1. Where in this case, it would be taking 32 seconds. Here it would be taking us 5 seconds. Now you see how this scales really well. That means when you start modeling really huge networks into one single neural network, the output is really the throughput gets really, really fast. So the project for this is hosted on GitHub. It is at github.com/akashgupta/neural electronics. I'm using JavaScript and a particular library called as brain.js for this. So if we take a look into the package.json, you can see that I'm using Brain and Synaptic. So these are two different neural network libraries that are available for JavaScript. Though they are not the very performant ones, they run on CPU. You can actually go ahead and use TensorFlow or any other Python-based library and take the advantage of having a GPU. But since this was the initial experiments were only based on smaller digital components, so did not have the. I just didn't want to do it that way. So if you take a look at this folder structure, we have something called as data, three folders: data folder, data generators folder, and the precomputes folder. Let's take a look into the data folder. In the data folder, we have 4-bit add in out JSON and other kinds of XOR, XNOR, or data. So this is the basic truth table represented in a JSON format, so that we can actually use the inputs and the outputs for this and train our neural network based on the inputs and outputs. And the same goes for 4-bit add in and out. That is, this represents 4-bit adder circuit that I have shown you previously. So these are all the inputs represented in arrays, and somewhere in the end of this file we have our outputs too. I think I missed it somewhere, but that's okay. So we do have the inputs and both outputs in a single file. So this is the data that is actually generated from the data generators. So we have I've just written a couple of data generators that will actually generate the data for a given type of input. That is to say, a 4-bit adder data. So this goes through simple brute force logic to actually generate the data for that. So I'm just using for 4-bit additions, I'm just using simple addition to generate the binary representation of the number, and also the binary representation of the number after being added. So you can find all the data generators in here, and here are the precomputes. These are a bit more complicated ones. These are the computed neural network data, that is the list of weights and the activation function that I've shown you. All those things are lie in this pre-computed data. So I've done a couple of tests on different kinds of 4-bit adder and 8-bit adder on this using different parameters, and I've generated a bunch of pre-computed networks. So if you remember the first AND gate example, there we have 0.4, 0.4, and the activation function will be 0.6. So you can actually train the data, and that is the main reason I've been using an external library. So the library was giving me the option to uh, capture the computed network data and export it into a JSON file. So, and here I have different kinds of training files. This is for training adders, this is for training OR, and this is for, I don't remember this one, what this one is for. Even this is for OR. I don't remember why I would sense this thing. Oh, so it's a simple perceptron. Okay, training to synthesize a perceptron, which in this case is an OR gate. Oh, or maybe it is word synaptic. So in some of the examples I've used brain.js, and in some of the examples I've used synaptic. That is why it is SYN. If you go to this JavaScript file, this is brain.js.